This is an addendum to the renal chapter, chapter 25. In that chapter, you saw this slide, that if we took everything that is filtered, subtract everything that is reabsorbed, and add everything that is secreted, we will end up with urine that is excreted. Remember that these three things happen in the nephron, and once the collecting duct reaches the minor calyx, the fluid in there is no longer called filtrate, it is called urine. By taking samples of the urine and of the blood plasma, and by measuring urine output, we can calculate what is called clearance. Now, clearance is defined as the volume of plasma that has a certain substance removed from it in a given time. And so it's milliliters of plasma per minute. The volume of plasma that has a given solute removed from it or cleared from it in a given time. We can, as I mentioned, use plasma concentration, urine concentration, and urine output to calculate clearance. So the clearance of a substance, we'll call it substance X, is equal to the urine concentration of that substance times the flow rate of urine. That's what V is, the volume of urine, that's mils per minute. And we'll divide that by the plasma concentration of a substance. We work these calculations in class. I will give you more practice calculations. All of this does not help you understand what clearance is. So let's look at the next slides and see if we can't, by using a similar game that we use in class with beads, if we can't demonstrate what clearance is. I'm going to add a point here to this slide. If you will recall, and if you will go through and work the renal physiology problem set that is posted under your labs for Unit 4, if you will work those problems, you will see clearance problems. You'll see them, you'll have to work them with regard to George, the last problem. You may also work a clearance problem with the third problem with the little boy named Robin. So apply the math, apply the bead game, and apply this tutorial. And hopefully you'll understand clearance. If not, come see me. We'll keep working it. There are certain substances that have been studied extensively enough that if we take a look at how they are handled by the nephron, we can use the clearance of those substances to estimate, for one thing, GFR. Now, there is a substance called inulin. Not insulin, inulin. This is a carbohydrate that is freely filtered in the glomerulus, from the glomerulus into Bowman's capsule, freely filtered, but it is not reabsorbed and it is not secreted. So it can be pushed through the filtration membrane into the filtrate, but the cells that line the nephron loops are not permeable to inulin. There is no mechanism embedded in the cell membrane, no protein that can transport inulin either out of the filtrate in terms of reabsorption, that can't happen, or from the plasma into the filtrate, as in secretion, that can't happen. The only thing that can happen to inulin in the kidney, in the nephron, is filtration. All right, let's take a look at this now, and I am going to add a few things. Here we see that there is 100 milliliters of plasma, and it has 4 inulin molecules in it. And we know that there could be another 100 mils right behind it in the bloodstream, and another, and another, and another. So here we are showing 500 milliliters of plasma that has a concentration of inulin of 4 molecules per 100 milliliters. There we see it here. Now, as this blood passes through the glomerulus, we have learned that the filtration fraction is usually right around 20% of all plasma. In other words, of all the plasma that runs through the glomerulus, 20% of it is going to be filtered. The rest will go chugging along into the efferent arteriole and the peritubular capillaries. Based on that, you can see that 100 milliliters of filtration, of filtrate, has 4 molecules of inulin, and that happens per minute. Now, what I can't show you here, compared to using the beads and this illustration in class, is, can you imagine that if we are indeed filtering 4 molecules of inulin in 100 milliliters per minute, that this box is now empty. This is plasma. And so that empty box, along with the other 80% of the plasma that comes into the glomerulus, is going to go chugging along to the peritubular capillaries. Now let me just say that there is no empty box of plasma in the bloodstream. We're just doing this to illustrate it. So we know that inulin is freely filtered, but it is not reabsorbed and it is not secreted. Therefore, this 100 mils of plasma has been completely cleared of inulin. The inulin clearance is 100 milliliters per minute of plasma. That's what makes clearance so hard. We're not talking about the inulin, we're talking about the amount of plasma that has inulin taken out of it. If we were talking about inulin, we would be using milligrams, not milliliters. Remember, we use milliliters when we're talking about a fluid and milligrams when we're talking about a solute. The only thing that happens to inulin is filtration. And for that reason, if we can calculate inulin clearance, we know what the glomerular filtration rate is. The only thing that happens to inulin is filtration. Therefore, inulin clearance is equal to glomerular filtration rate. Let's look at how the kidney handles glucose. We already know a lot about this, but let's do it with respect to clearance. So, very similar scenario. We have 4 molecules of glucose per 100 milliliters of plasma. Boom. Same thing, right? That gets filtered, and we now have 4 molecules of glucose per 100 milliliters of filtrate. That solution passes through the tubule, and we know that all glucose under healthy circumstances is reabsorbed. This box is not empty. It's not even partly empty. And so we say that the clearance of glucose is 0 milliliters per minute. No glucose is excreted. Now, how are we going to use this information? Well, we know that in this scenario, GFR is 100 milliliters per minute. The only thing that happens to inulin is filtration, and that's how we have calculated glomerular filtration rate. We know that glucose clearance is 0 mils per minute. If the clearance of a substance is lower than GFR, we know, based on glucose, we know it has to be reabsorbed. And we say it is net reabsorbed. In other words, we're not sure, but there might be of substance X. We're sure about glucose, but other substances might be secreted a little bit and reabsorbed a little bit, eliminating the influence of the secretion. So we would say net reabsorbed. If the clearance of substance X is lower than GFR, we know there is net reabsorption. Here's another interesting scenario using urea. Urea is a small lipid-soluble molecule, which means it can passively cross membranes and will do so to equilibrium. Knowing that, here we can see 4 molecules of urea per 100 milliliters. Freely filtered. Now we have 4 molecules of urea per 100 mils of filtrate. The rest of the blood goes chuck, 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 chuck around, and urea will move back into the bloodstream to equilibrium. So we would end up with just 2 molecules here, and here you can see 2 molecules back in the plasma. Okay, so if that's the case, if we end up with 2 molecules here and 2 molecules in this 100 mils, we see that the urea clearance is 50 mils per minute. Only half of the box has been emptied of urea. The box represents 100 mils. Half of it is empty, so 50 mils per minute is urea clearance. Let's double check something. If the clearance of urea is lower than GFR, is it? Are you sure? Yes, here. GFR is 100. We proved that in the first slide. So the clearance of urea is 50 mils per minute. That's lower than 100 mils per minute. What do you know about how the kidney handles urea? If your answer is there is net reabsorption, you are absolutely correct. Let's take a look at one more scenario, this time using penicillin. Now, this is pure penicillin. It's not the kind of penicillin that is used today. The penicillin that is administered today is attached to a protein that can't cross the tubule cells. Okay? So we're just looking at penicillin in its original form. In its original form, penicillin, and again we are repeating our scenario, 4 molecules per 100 mils of plasma. That gets freely filtered. So now we have 4 molecules of penicillin per 100 milliliters of filtrate. The rest of the plasma goes chugging along. And from this scenario, we can see that there is penicillin that is secreted. None of it, there's no reabsorption that we know of, so there is net secretion. Here we have our first 100 milliliter box that's empty. And here we have a second box that is half empty. We can say that the clearance of penicillin is 150 milliliters. So, if the clearance of penicillin is greater than GFR, what do we know about the kidney handling it? If you chose that there is net secretion, you are correct. We can say this about any substance. Substance X clearance is greater than GFR, we know there is net secretion. If substance X has a clearance that is lower than GFR, we know that there is net reabsorption. And if the clearance of substance X is equal to GFR, we know that the only thing that the kidney does is filter it. Okay? Now, you may need to go through these slides several times. I encourage you to use the bead game that I make available in class. If you need more time with it, I can leave you with it in the hallway to work with that, or in another classroom. I won't give it to you to take home. I've lost too many of these. But if you need to work with the bead game again after watching this, I hope you will.